Welcome to part 2 of the Formal Languages and Automata course. In the last lecture, I promised you that we would be studying the following question from a variety of angles. In particular, how do we know when a string S is a member of a language L? A naive way how to approach this problem would be to enumerate all the elements of the language L. We would therefore arrange all the elements in language L one after the other, say S1, S2, S3, so on and so forth. And then you would compare string S with the first element, S1. If it is indeed the same string, you return yes. Otherwise, you move on to string S2. And you keep on going till you reach the end of the enumeration. If you reach its end, you can then just return no, meaning that S is not part of your language. Now clearly, this only works when L, your language, is finite. When your language L is infinite, there is the risk that you keep on going forever and ever without ever returning an answer. Now this is a problem because a number of languages that we use every day are indeed infinite. Say, take for example your favorite programming language. It has an infinite number of programs that belong to it. This means that a proper treatment of this membership question requires us to consider infinite languages. But how do we reason about infinite sets? Consider the infinite set of string sigma star defined over some alphabet sigma. The first step towards reasoning about this infinite set is to panic uncontrollably. The second step is to realize that every string in this infinite set has a finite structure. Moreover, the structure is regular, meaning that there is a pattern that repeats itself. More concretely, if you pick any string S in the language sigma star and you process it from left to right, that is, you look at it from the left-hand side, you will see either of two cases. Either S is an empty string, or it has an element alpha that belongs to sigma in front, followed by a continuation T. T again would have a similar structure. The fact that S is finite in structure means that you cannot keep on taking option 2 forever, and eventually you will hit the empty string. But how is this fact useful when you are processing infinite sets? Let me show you how. Assume that I want to define a function called size that takes any string in my set sigma star and returns a natural number denoting the size of the string. This means I have to define a mapping from every element in sigma star to some natural number. How do I do it? Any string S in sigma star has either of two forms. If it is the empty string, I just return 0. If it is, on the other hand, of the form alpha followed by some continuation S, I return 1 plus the size of the continuation S. Surprisingly, this does the trick, and it suffices to define a function for any element in sigma star. If you don't believe me, and you shouldn't, let's pick an arbitrary string from sigma star, and let's see how size works over it. Let's pick, for example, the string ABB. What is the size of ABB? Well, ABB is of the form alpha followed by some continuation t. So we have to take the second case of the definition. And this tells us that the size of ABB is 1 plus the size of BB. What is the size of BB? Again, we map this structure of the string with the second case. And this means that the size of BB is 1 plus the size of B. What is the size of B? Again, the string B has the form alpha followed by some continuation t. Therefore, we have to take the second case. And this means that the size of B is 1 plus the size of the empty string. What is the size of the empty string? Well, in this case, now we have to take option 1. And this means that the size of the empty string is 0. Therefore, the size of ABB is the summation of all these numbers, which gives us the number 3. But one swallow doesn't make a summer. What if I got lucky? Can I do it again? Let's consider another example. For instance, what if I wanted to find the function number of occurrences of A in a string from a sigma star? Once again, I have two possible cases. If my string is of the form empty string, I just return the value 0. If, on the other hand, my string is of the form alpha followed by some continuation s, then what do? Then I tell myself, if my alpha is equal to the alphabet A, then I just return 1 plus the number of A's in the continuation S. Otherwise, I just return the number of A's in the continuation S. If you don't believe me, I will let you calculate the number of A's for the string A, B, B, A. But two swallows don't make a summer either. Let's consider yet another example. This time, let's try to define a predicate function. A predicate is a function that maps to the Boolean domain B. This function, I'm going to call it has B, and essentially it returns true if my string has at least one occurrence of the letter B. Otherwise, it returns false. So, if I take an arbitrary string from sigma star, once again, it has either of two structures. If my string is empty string, I return the value false, because clearly the empty string has 0 occurrences of the letter B. If, on the other hand, my string is of the form alpha followed by some continuation s, I have two further subcases to consider. If alpha is equal to B, then I'm done. Then I have found one occurrence of B. So then I can just return true. What if alpha is not B? Then I still haven't found an occurrence of B. So then I have to continue processing the continuation of the string. This means that the else is defined as B of the continuation S. You don't believe me that this works? I will let you calculate the function or the value for the operation has been over the string AB. Let's consider one final example. Consider the endo function filter B that takes a string and strips out every occurrence of the letter B in that string. Endo function is a very sexy word that I highly recommend that you use it for your next date. How would I define this endo function? Well, any string in sigma star, once again, has either of two cases. If S is the empty string, then I have nothing to strip away, and I just return the empty string itself. If S is of the form alpha, followed by some continuation S here, what do I do? Then I have two cases to consider. If alpha is a B, then what? Then this means that I have to strip away this B. Then I just return the filter of B of the continuation. Otherwise, else, this means that my alpha is not a B. So then what do? I just return alpha cons the filter of B of the continuation S. Once again, this definition happens to work. If you don't believe me, try it out on the string AB, or any string of your liking from the set sigma star. It should work.